Hi, welcome back to my channel, and for today's video, for the complex analysis series, we will be talking about derivatives of complex valued functions. So I just want to let you know that this topic that I will be discussing is one of the most useless topic to be taught in school. Joke, I'm kidding. Anyway, this is actually a complex analysis. So that means one big application for complex analysis is that we can do that in engineering, physics, and so many sciences that are almost related to mathematics. So I just want to let you know that if you have any questions or clarification, you can comment down there so that I would know and we can discuss on that. And guys, thank you so much for your undying support. And if you are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. So we will start now. So what's really derivative of complex valued functions? So given that you have a function f whose domain of definitions contains neighborhood of point z sub 0. So meaning to say that your z sub 0 here is a complex number, and that when you take the modulo of z minus z sub 0, that's always less than to the epsilon. Your epsilon here is a positive number. The derivative of f at z sub 0 is the limit, this one. Okay, so that means it's a formal definition for the derivative of a complex valued function. So that's limit of f of z minus f of z sub 0 all over z minus z sub 0 as z approaches z sub 0. So, and the function f here is said to be differentiable at z sub 0 whenever this f prime of z sub 0 or the derivative exists. So, if we express this definition of the variable z in terms of the new complex variable, let's say we have the delta z, and in this case the delta z is z minus z sub 0. Of course, your z here is not equal to z sub 0. Then we can rewrite the above definition by f prime of z sub 0. That's equal to the limit of f of z sub 0 plus delta z minus f of z sub 0 all over delta z. And in this case, your delta z converges 0, approaches 0 rather. So if we relate this into this new form here. And always note that since our f here, so our f here is defined throughout the neighborhood of z sub 0. So your number here, which is the f of z sub 0 plus delta z, is always defined for the modulo of delta z that is sufficiently very small. How do we show that by a geometric interpretations? If you have here the complex plane, so given that you have, let's say, a point here and another point here. So in this case, this is actually our z sub 0, and this is actually our z sub 0 plus delta z. Your epsilon is actually the estimated length of the radius that can form a circle. So you have your delta z here. So the distance here is delta z. Okay, so if we write, instead of writing f prime of z, if we write this in this way, dw over dz, this equation here, this one here, let me label this one as equation 2. The one that is presented here is actually equation 1. So if we write this in this way, then this equation 2 can be written as this. That's limit of delta w over delta z as delta z approaches 0. Okay, so that's another way of representing how our derivative of a complex valued function is. So if you have any question or clarification, kindly let me know so that we can discuss that. Okay, so let's consider an example here. Suppose we're interested of this f of z, which is equal to z squared. So at any point z, we have the limit of delta W over delta Z as delta Z converges 0. That's technically the same as the limit of Z plus delta Z. In this case, this is squared minus Z squared over delta Z as delta Z approaches 0. So why is this again? Because the definition of our function is f of Z equals Z squared. So in this case, we substitute this one thing here because this is Z plus delta Z. In this case, so we have this one, and this is actually f of Z, so we have this one. If I'm gonna simplify this, I would end up having limit of, okay, so let me do the basic elementary algebra here. So that's Z squared plus 2Z times delta Z plus delta Z squared minus Z squared all over delta Z, and this delta Z approaches 0. So what happened here is this will be cancelled. I'm gonna factor this out. What we left here is 2Z plus delta Z. So therefore this will be cancelled. So what you'll have is the limit of 2Z plus delta Z as delta Z approaches 0. Now, if you observe on this is already a linear function in terms of the variable delta Z. So we're done this on the previous video on how to get the limit for this. So you'd end up having 2Z. So that's the derivative of the function f of z equals z squared. Okay, so let's consider another example here. Let's say our f of z here is equal to z bar. Then what happened? Observe that delta w over delta z, we can have this as z plus delta z bar minus z bar over delta z. Observe that the conjugate of two complex number is actually the conjugate of the sum of two complex number is actually the sum of the conjugate. So I can have this as z bar plus delta z bar minus z bar over delta z. So I have left with delta z bar all over delta z. Now, what if we really have to goal in this case that there should be a limit on this? So let's double check in this one here. Assuming that the delta z is actually the same as delta x delta y. And suppose that we let this assume to the origin, so that's 0, 0, vertically. So that means when we say vertically, that's 0 delta y, or simply the imaginary axis. So that means to say, if you have a geometric representation for that, you want the function to be approaching to the origin on the imaginary axis. Because always remember that when we take the derivative of a complex function, we're actually considering all the directions. This is typically different from the derivative of real, because when we observe or evaluate for real numbers, we only focus on the right, which is the right side of the origin and the left side of the origin. However, in this complex valued function, we take all the possible direction. It could be like this, like that, or you can have this way, all the directions on the complex plane. So in this case, we will try to consider the delta z that approaches to the origin in the vertical manner. So that means when it's the vertical manner, we assume that the delta x here is 0. Okay, so what happened? So our delta z in this case is the same as the delta z bar is the same as 0 plus iy, and this is basically 0 minus iy. And if you notice, this is just the same as negative 0 plus iy, which is equal to negative delta z, which means to say that delta w over delta z is actually negative delta z over delta z, which is equal to negative 1. So that is when we work on the imaginary axis. Like now, let's try to compare that when we work on the real axis. So that means to say, we try to approach to the origin horizontally. So it's in horizontal manner. So when it's horizontal, our delta y is 0. Okay, so we have delta x 0. So this is now our real axis. So in this case, we work on this. Let me use the red one. Okay, so we approach on the origin. So therefore, we have the delta z bar. This is the same as delta x plus I0. So this is simply delta x minus I0. And this is just the same as delta x plus I0. This is equal to delta z. Meaning to say that the delta w over delta z is delta z over delta z. And what happened then? This is equal to 1. So meaning to say that when we try to approach to the origin, when we start with the imaginary is actually different when we do in the real. So therefore, they don't have the same sided limits. In other words, this w over dz or the derivative does not exist. Okay, let's consider another example. We have f of z equals the square of the modulo. So meaning to say that if you have delta w over delta z, that's actually the whole over, that's delta z. Recall that if you have a complex number z, that's square of the modulo, that's the same as z times the conjugate of z. Okay, so that's on the video I have uploaded long time ago, so you might want to check on the thumbnail here for this property. Okay, so I would have now z plus delta z times the conjugate of z plus delta z, and that's z times the conjugate of z all over that's delta z. And remember, this will be z plus delta z times z bar plus delta z bar. Okay, and what happened, I would get z bar plus, I would have z bar times delta z, and I would have plus z times delta z bar plus delta z times delta z bar. And if I'm gonna include this one thing here, so I have z minus z bar. So this will be cancelled here. So what you left is three terms here. So I can write, and these three terms, if I'm gonna divide that by delta z, I would have z bar plus, I'm gonna take this first, so I would have delta z bar, and then I would get plus z, delta z bar over delta z. I would now evaluate this for case 1. So case 1, if z approaches the origin through the, let's start with the real axis. So that means delta x 0. So what happened then is your delta z bar is actually delta x plus I0. And this is actually delta x minus I0 or delta x plus I0, and this is delta z. So meaning our delta w over delta z, which in this case is z bar plus delta z bar plus z. In this case, that's delta z over delta z. So this will be just 1. So finally, you would have z bar plus delta z bar plus z. Case 2, when z approaches the origin through 0 delta y. So that means on the imaginary axis. So that's delta z bar, and this is delta x, I'm sorry, it should be 0. 0 plus I delta y. And this is actually 0 minus I delta y. And this is actually negative of 0 plus I delta y. And this is actually negative delta z. So meaning to say that your delta w over delta z, this is z bar plus delta z bar plus z. Your delta z bar in this case is now negative delta z over delta z. So this is negative 1. So you would have z bar plus delta z bar minus z. And also you can check that on the above, this is actually z bar, and this is actually plus delta z plus z. However, in this case, this is z bar minus delta z minus z. So what happened? By uniqueness of the limit we've discussed on the previous video, I would have z bar plus delta z plus z, this is equal to z bar minus delta z minus z. So that means I equate these two here because of the uniqueness of the limit. So this will be cancelled, and then I would end up jumping into conclusion that my z is 0. So what's the moral of this example? This implies that our derivative cannot exist when your z is not 0. So meaning it only exists when z is 0. So what's the implication of this? That for the previous example, we are actually solving for the derivative, and we can be able to take a derivative at some different values of z. However, in this case, this last example, we are actually restricted that the derivative only exists when z is 0. So the implication of this, we will find it out on the next video. So I hope you learned for this basic introduction for derivatives of complex function. So if you have any questions or clarification, don't forget to comment so that I would know and we can discuss on that thoroughly. So that's all for now. Thank you so much for watching. So if you have any question or clarification, let me know, and I'll be more than willing to help you with that. Thank you guys, and don't forget to be updated on my channel by clicking on the subscribe button. Have a great day.